Hello friends, I welcome you all once again. This is Dr. Gajanan Zadav. Here in this video, today we are going to discuss about interferometer. What is interferometer? What are the types of interferometer? And we will study the first type it in detail, that is Michelson's interferometer. So let us talk about what is interferometer. Interferometer is an instrument in which the phenomenon of interference is used to make precise measurements of wavelength or distances, refractive indices, testing of optical components, mechanical displacements, etc. It is an optical instrument which is used for measuring the flatness and determining the length of slip gauges. The wavelength of light used for measuring unit, it is based on principle of interference. It is also used to overcome the limitations of optical flat. So this is all about the interferometer. Now what are the types of interferometer? Basically there are different types of interferometers. So here the first type is Michelson's interferometer, and the second type, that is Fabry-Perot interferometer. In this video we will discuss Michelson's interferometer in detail. So what is Michelson's interferometer? Michelson's interferometer consists of these few components. That is, there will be an extended source of light, two mirrors will be there, glass plate will be there, and one detector will be there. So this is how the Michelson's interferometer consists of different components. The Michelson's interferometer is two beam instrument, while Fabry-Perot ethalon is a multiple beam instrument. Interference involved in both the instrument is based on division of amplitude. In simple way we can say, in Michelson's interferometer, two beams are used, and in Fabry-Perot interferometer, multiple beams are used in that instrument for getting the interference in both the instrument, which is based on division of amplitude. So this is what we call it as a Michelson's interferometer. Now on which principle this particular Michelson's interferometer works? The amplitude of the light beam from an extended source is divided into two parts of equal intensities by partial reflection and partial refraction. These beams are sent into two directions at right angles to each other and are brought together after reflection from plane mirrors to produce interference fringes. This is the principle on which Michelson's interferometer works. The two interfering beams are formed by division of amplitudes. The amplitude of light beams from an extended source is divided into two parts of equal intensities by partial reflection and refraction, and these beams are sent in two perpendicular directions. The two beams are finally brought together after reflection from plane mirrors to produce interference fringes, and this is the principle on which this Michelson's interferometer works. Now how this Michelson's interferometer is constructed? Let us talk about the apparatus. Now if you look at this particular apparatus, then you will find that here there is an extended source. This is one of the mirror. This is mirror M2. There are two glass plates C and glass plate D. Therefore, there are two mirrors, that is M1 and M2. Front silver plane mirrors. M1 is the mirror which is fixed, whereas M2 is the mirror which can be moved parallel to itself by means of a very sensitive micrometer screw, which we call it as a movable mirror. C and D, these are nothing but the two plain glass plates, parallel glass plates of equal thickness, whereas C is called as the beam splitter. That is, a beam which is incident from the source of light on C is partially reflected and partially transmitted. That means this beam is splitted into two beams. That's why it is called as a beam splitter. Whereas D is called as the compensating plate. So this is how this particular apparatus is. Now let us talk how this Michelson's interferometer works. Now if you look at this particular diagram, then you will find that the working is very simple. There is an extended source which emits the light beam. It falls first on this particular glass plate C. After falling on this glass plate, it gets split into two parts. That is, one beam of this light will get reflected and will fall on M2, and second will get transmitted and it will fall on M1, and then again they gets reflected back. So a ray of light falls on the glass plate C at an angle of 45 degree, which is kept at an angle of 45 degree. It is then partly reflected and partly reflected. The reflected beam moves towards mirror this M2 and gets reflected back in the same direction. On the other hand, the transmitted beam falls on the mirror M1. The two emergent beams have been derived from single incident beam and are therefore called coherent beam. The two beams produce interference under suitable conditions. Now here, the function of compensating plate D. The reflected ray passes through C thrice. That is, when this particular light falls on light beam forms on C, then it gets split into two parts. So once this reflected beam travels and falls on M2, again it gets reflected back and again it transmitted through it. So this is how the reflected ray passes through C thrice, but the transmitted ray AB passes through C only once. That is why a second light beam plate D of the same thickness and inclination as C is introduced. Thus the function of the plate D is only to equalize the optical path traversed by the both beams. That means to overcome the optical path difference, we are using the compensating plate. So that's why we call it as a compensator. So this is how the Michelson's interferometer works. Now, types of fringes. There are different types of fringes obtained. Circular fringes are obtained, straight fringes are obtained, and white light fringes are also obtained. Now, let us talk about circular fringes. If you look at this diagram, then you will find that there are two mirrors, M1 and M2. When this mirror M1 and M2 are mutually perpendicular to each other, then concentric circular fringes are obtained. When M1 and M2 are kept mutually perpendicular to each other, then and then only we will get circular fringes, or circular fringes are observed. The image of M2 is at M2 which is parallel to M1, and hence M2 and M1 form the equivalent of a parallel thin film. The circular fringes will be situated at infinity. Therefore, they can be observed by a telescope focus for infinity. Thus, we get circular fringes of equal inclination or Heidinger's fringes. Now, second, straight fringes. If M1 and M2 are not exactly perpendicular, then a wedge-shaped air film will be formed in between M1 and M2 The film becomes practically straight when M1 actually intersects M2 in the middle. The fringes are fringes of equal thickness, and this is how we are getting the straight fringes. This is how we are obtaining the straight fringes over here. So remember, if M1 and M2 are not exactly perpendicular, then we are getting the straight fringes. Third type, that is white light fringes. If white light is used, in the central fringe will be dark and other will be colored. With white light fringes are observed only when the path difference is small. These fringes are important because they are used to locate the position of zero path difference. Now, what are the applications of Michelson's interferometer? There are various applications of Michelson's interferometer. The first one is that it is used to determine the wavelength of monochromatic light. Precision measurement of wavelength is done with the help of Michelson's interferometer. Second one, that it is used to determine the difference in wavelengths of spectral lines. Third one is that it is also used to determine the fine structure of spectral lines. Then it is also used to determine the thickness and refractive index of transparent material. Michelson's interferometer is also used to evaluate the standard meter. That is, measurement of a standard meter in terms of standard wavelength is done. Michelson's determine the number of times the wavelength of monochromatic light, like cadmium red, blue, green, was contained in a standard meter. So for that purpose also Michelson's interferometer can be used. Then width of spectral lines, that is, it can be used to determine the width of spectral lines also. If a source of light consisting of two wavelengths lambda 1 and lambda 2 which differ slightly is used, then two sets of fringes corresponding to the two wavelengths lambda 1 and lambda 2 produced in a Michelson's interferometer. So these are different applications of Michelson's interferometer. Now, how to determine the wavelength of monochromatic light? Using monochromatic light radiation of unknown wavelength lambda, the interferometer is adjusted for circular fringes. That is, how do we adjust for circular fringes? Simply M1 and M2 are kept perpendicular to each other. So this is first done. Then with any ring at the center, the reading of micrometer is noted. Let it be x1. Now the mirror M1 is moved with the help of micrometer screw. And when we move this micrometer screw with the screw mirror M1, the fringes will appear to sink or rise due to the change of path difference. Let n is the number of fringes which are, or n number of fringes are moved, and x2 be new reading of the micrometer. When the mirror moves through a distance lambda by 2, one fringe shifts, and hence x2 minus x1 can be written as x, and this and again be written as n into lambda by 2. Let us consider this is an equation number 1. Lambda is equal to 2 of x2 minus x1 divided by n, or again we can write here lambda is equal to 2x upon n. Thus, this is the equation with the help of which we can determine the wavelength of monochromatic light. Now next, how to determine the difference in wavelength between two neighboring lines. Here, let the source of light emits two close wavelengths, lambda 1 and lambda 2, like sodium D lines, where lambda 1 is greater than lambda 2. If however the bright rings due to lambda 1 coincide with the dark ring due to lambda 2, the ring system would disappear, producing uniform illumination. This is called as the dissonance. So dissonance is the position of maximum indistinctness. Now, if however the bright rings due to lambda 1 coincide with the dark rings due to lambda 2, the ring system would disappear, producing uniform illumination. This is called dissonance. This is the position of maximum indistinctness. Therefore, for dissonance, 2x is equal to n into lambda 1. This can be written as n plus 1 lambda 2. Or n can be written as 2x upon lambda 1 and n1 plus n plus 1 2x by lambda 2. Or therefore 2x by lambda 2 minus 2x upon lambda 1 can be written as 1, and this ultimately can be written as lambda is equal to mean wavelength, and it can be written as d lambda is equal to lambda square upon 2x. So this is the equation for